You've probably heard of things like ChatGPT, right? Well, a huge reason they work so well is an algorithm called Proximal Policy Optimization, or PPO. It's one of the cornerstones of modern AI, but what does it actually do and how? Well, today, we're going to pull back the curtain and demystify PPO, breaking it all down step by step.
So here's our game plan. We're going to start with the absolute basics. What even is reinforcement learning? Then we'll get into how AI agents learn using something called policy gradients. From there, we'll see a big problem that crops up, the step size problem, and how an older algorithm called TRPO tried to fix it. That's going to set the stage perfectly for PPO's big idea. And you'll want to stick around for the end, because we're going to finish with a pretty surprising twist about what really makes PPO so effective.
All right, so reinforcement learning, or RL for short. At its heart, it's all about learning by doing. I mean, think about how you teach a dog a new trick. You tell it to sit, it sits, you give it a treat, right? Well, RL is basically that, but for computers. We're training an agent to figure out how to master a task through trial and error, all in the hunt for rewards.
And this little feedback loop you see here, this is the absolute heart of reinforcement learning. The agent does something, it takes an action, the environment changes because of that action, and then the agent gets feedback, a new state, and a reward. And it just keeps doing this, over and over, learning from the outcomes. To really get it, though, we need to break down those key pieces: state, action, and reward.
First up is the state. You can think of this as a complete snapshot of the agent's world at one exact moment. So, for a chess-playing AI, the state would be the exact position of every single piece on the board. It's all the info the agent has to work with. Okay, next we have the action. These are the choices the agent can make. So, back to our game example. If the agent is playing Tetris, its actions are pretty simple, right? Move the block left, move it right, or rotate it. From any given state, the agent has a whole menu of possible actions it can pick from.
And how does the agent know if it made a good choice? That's where the reward comes in. It's the feedback. It's literally just a number. A positive number, the reward, is like the environment saying, "Hey, good job, do more of that." A negative number, or a penalty, says, "Oof, bad move, try to avoid that in the future." Clearing a line in Tetris, that's a nice positive reward. The game ending, that's a big fat negative one.
And finally, we get to the policy. This is the big one. The policy is the agent's brain. It's the strategy it uses to look at a state and decide which action to take. And really, the entire goal of reinforcement learning is to find the best possible policy, the one that will get the most reward over the long haul. So, the million-dollar question is, how do we find this amazing reward-hoarding policy? Well, here's a cool way to think about it. Imagine you're on a giant mountain, and the higher you climb, the more reward you get. The very top of the mountain, the summit, is the maximum possible reward. Our job is to find the path that gets us to the peak.
Now, in modern AI, our policy is almost always a neural network. And you can think of a neural network as having a bunch of adjustable knobs or parameters. We call these parameters theta. Our whole mission is to tune these knobs just right to maximize our reward. We're looking for the settings that create the policy that leads to the best outcomes again and again.
Okay, so we're on this reward mountain, but how do we know which way is up? I mean, it could be foggy, right? Well, that's where the policy gradient theorem comes in. It's like our compass. It calculates something called the gradient, which is just a fancy way of saying the direction of the steepest path uphill. It tells us exactly how to tweak our policy's knobs to take actions that lead to even bigger rewards.
So just follow the gradient and march uphill. Sounds easy, right? Well, not so fast. It turns out the size of the steps you take really matters. If you take one step that's just a little too big, you could go right over the edge of a cliff and tumble all the way back down. This is what we call the step size problem, and it's a massive hurdle in RL.
And this right here is the fatal flaw of the most basic policy gradient methods. A single, overly ambitious update, one bad step can cause your policy to just completely forget everything it's learned. Performance doesn't just dip a little, it can catastrophically collapse, wiping out hours and hours of training in an instant. And if you want to see what that looks like, check out this graph. This shows the danger in action. You can see performance is all over the place. It might suddenly spike up, which is great, but that success is super fragile. One wrong move, one step that's too big, and boom, it all comes crashing down. We need a safer, more reliable way to climb this mountain.
So the first real attempt to solve this stability problem was an algorithm called Trust Region Policy Optimization, or TRPO. And really, the name kind of gives the whole idea away. It's all about making updates that you can actually trust not to blow everything up.
Basically, TRPO gives our mountain climbing agent a safety rope. It creates this imaginary bubble around our current policy called a trust region. It's a safe zone. And the algorithm mathematically guarantees that any step taken inside this bubble will be an improvement. By limiting how big each update can be, it stops the agent from accidentally falling off that cliff.
So TRPO works. It's stable, it's safe. But there's a huge catch. It is an absolute beast to implement. The math it uses to create that safety rope is incredibly complex and computationally expensive. It was a great idea, but it created this huge barrier for researchers. The world needed a new hero, an algorithm that could be just as stable as TRPO, but without all the complexity. And that's where our hero, PPO, enters the scene. Proximal policy optimization was designed to be the best of both worlds, to get that same amazing stability that TRPO had, but with a much, much simpler and more elegant approach.
And the brilliance of PPO really is its simplicity. It manages to deliver that same TRPO-level stability using way simpler math. Instead of building this complicated mathematical safety net, it just cleverly tweaks the goal itself to naturally discourage those big, risky steps.
Okay, so how does this magic clipping actually work? It's pretty cool. First, it just compares the new policy to the old one. Now, if the agent finds a really good action and wants to make it way more likely, PPO steps in and clips that update, preventing it from getting too overenthusiastic. Same thing in reverse. If it wants to make a bad action way less likely, PPO clips that too, to avoid overcorrecting. The end result is that every single step is a safe, conservative, and reliable improvement.
And here it is, the secret sauce in mathematical form. That little min and clip you see right there, that's it. That's the whole trick. That simple function enforces that don't step too far rule we've been talking about, giving us all the stability of TRPO without the massive headache. It's an incredibly elegant solution that totally took the AI world by storm. But is it the whole story? So this is where our story takes a really interesting turn. For years, pretty much everyone believed that this clever clipped objective was the key innovation. It was the reason PPO was so successful. But it turns out the beautiful theory might not be the whole story after all. In 2020, a paper called Implementation Matters dropped a bit of a bombshell on the PPO narrative. What they found was that a huge chunk of PPO's amazing performance didn't actually come from its famous core algorithm, but from a bunch of small, seemingly boring code-level optimizations. So here's the big twist. PPO's fame is built on this really clever, elegant clipping idea. But when researchers started digging in and stripped away all the little implementation details, things like reward scaling and value function clipping, they found that the clipping mechanism alone didn't explain its success. It turns out the real unsung heroes were all these tiny engineering details in the code that make all the difference.
And that leaves us with a really fascinating question. Is PPO's incredible success a triumph of elegant theory, or is it a story of clever practical engineering? The truth, as it often is that it's both. And it's a powerful reminder that in the world of AI, sometimes the small, unglamorous details are the biggest ideas of all.